Hi everyone, my name is Tianqi Chen from University of Washington. Today I'm going to tell you about how do a optimized machine learning system use machine learning. This is a work done in collaborating with many folks here in University of Washington. So 2 years ago, one of my friends in computer architecture comes to me to say, hey Tianqi, I'm working on this awesome deep learning accelerators. Do you want to work together? I said, sure, that sounds awesome. How do I put my favorite puppy detector on top of it? Then I get this whole page of micro-assembly code on how to program that deep learning accelerator. You don't have to read it, but from the far look at it, you can tell it's not fun to do the job. I had quite a lot of painful experience doing that. You can tell, some of the audience can already know that I'm not alone in a sense that this is a problem that's pervasive in today's deployment or training story of deep learning software. As a matter of fact, machine learning has become so important that there are explosive amount of frameworks and models being around that want to deploy. And meanwhile, there's also explosion of hardwares that want to deploy our smart application to, including your data center, CPU, GPUs, your mobile devices, embedded IoT devices, and TPU-like accelerators. There's a huge gap between the software high-level models and hardware they want to deploy. And this is exactly a problem we want to solve today. So before I talk about solution, let me tell you about what existing works do. So if you take a look at existing deep learning models, like what Philip said, most of the existing deep learning model will represent the computation of the existing deep learning in this what called computational graph or data flow graph, where each of the nodes in data flow graph are primitive tensor operators, such as high-dimensional convolution or matrix multiplication. In order to offload them into a low-level hardware like NVIDIA devices, usually what existing framework do is they will rely on low-level libraries. In case of NVIDIA, there's a library called CUDN that optimize each of the node tensor operators of the data flow graph. Under the hood, actually, there's more things going on. So for each of the tensor operators in the computational graph, there's an engineer somewhere or a team of engineers spending time trying out different variants of the code running on the hardware, like trying out loop tilings for CPU locality or map them to accelerators. There are many more things that being tried out in here. So what is the problem of this approach? Well, one of the problems that you may notice is that for every operator in the high-level computational graph, they have to be implemented in the low-level compute library. Now, as a system researcher, there are a lot of things that you can do. And actually, in order to implement those three operators, I can tell you there are definitely more than 3 people behind. But I'm just using 3 to represent the kind of engineering effort that you need to spend on that. So if you want to do system optimization, one of the common optimizations that you can do is that you can take 2 of a node or 3 of a node in computational graph, you fuse them together into another computational node that saves you the global memory load, and usually that gives you 1.5x speed up over the normal workload. The problem now is actually you find we get a new computational node called Blue node that's not available in a low-level library. As a matter of fact, most of the existing deep learning frameworks avoid doing such optimization because they are restricted by the count operator that's provided by a low-level library. Of course, one possible solution to this problem is that you just assign another engineer to code that up, but that means another turnaround time. Let's try to multiply that by the amount of hardware that you support, and you can imagine there are a lot of things going on that you don't want. And actually, as a graduate student, I don't have that many manpower on my disposal to solve this problem. So we will need a completely different approach. We call the approach learning-based learning system. The idea is simple. We want to replace the general effort of human-based exploration by an automated system. The system contains 2 important components. The first component is hardware-aware search space of the optimized programs, and then there's a machine learning-based component that explores the space to give you the best program for each tensor operator. Noticeably, we can directly generate optimized operators without relying on those low-level libraries, so we are no longer at the mercy of what the low-level library provides you. I will talk about these 2 components in more detail. So in order to represent a hardware-aware search space, it's very important to remember that we are competing against highly experienced human engineers. And we really need to build a search space that can represent the state-of-art optimizations that you can get from those engineers. So we built a tensor expression language that describes the high-level computational workload. And then the general idea is we will define a search space that consists of all the possible optimizations that you can throw on to optimize your workloads on the target hardware. This is the idea that borrowed from the image processing language Halide. The challenge here is that for different hardware, we need to consider different characteristics. For example, in CPU, you might want to do some loop transformation to take benefit of memory locality or vectorize your code. There are more hardwares they want to consider, including GPUs, or even more interestingly, TPU-like accelerators are emerging. So for GPU case, one of the important characteristics is that GPU usually have an explicitly managed shared memory. And it's very important to build in primitives such as cooperative fetching or make effective memory use through shared memory to actually take benefit to maximize the GPU utilization. The problem becomes even more interesting if you take a look at TPU-like accelerators. The challenges are in twofold. The first is in terms of the compute primitive that this TPU-like accelerator provide. Traditionally, if you program your code, you will express how do you program each element, how do you compute each element in your target computation. This is like a scalar program. If you take a look at modern processors, that's usually vector instructions like SSE, AVX 512, that allows you to compute things in vector form. If you take a look at TPU-like accelerators, one key characteristics of this accelerator is that they have tensor instructions that takes high-dimensional tensor as basic instruction operands. Even more challenging part is that there's no standard on what this tensor instruction should look like. So maybe one variant of TPU will have a matrix multiplication as a basic tensor computation instruction. The other accelerator will have one-dimensional convolution as a basic primitive. It's very important to take benefit of these primitives in order for your application to actually run on those devices. So how do we solve this problem? We use the same tensor expression language to allow the hardware designer to declare the semantics of the tensor intrinsic that's provided in their accelerator. And we have a tensorization primitive that tries to transform the original program to take benefit from the tensor intrinsic that's provided by the target hardware. The second challenge actually lies not in the compute, but the memory subsystem in those TPU-like accelerators. Usually, each count of this accelerator have explicitly managed memory that requires you to explicitly load the memory using DMA instruction to your specialized memory and run the TPU and run the tensor intrinsic computation. As you know, in order to keep your compute fast, you kind of have to make your memory keep up with the compute. And ideally, you want to overlap your memory load with the compute. The problem of specialized accelerator is that usually they don't have very smart cache that helps you to automatically prefetch things. And you have to bake in those explicit instruction dependencies into your instruction stream. I don't have time to talk about the detailed solution, but you can check our paper. We have a solution called virtual thread lowering that lowers a high-level multi-threaded program onto those low-level explicit dependent program that can be handled by software in the TPU-like accelerators. So to summarize, in order to build a hardware-aware search space, we want to make use of all the possible optimization knobs available and put them into our system. We include existing available knobs from previous works and introduce novel knobs to actually improve GPU performance and enable TPU-like accelerator performance. The combination of all those possible choices actually gives you a search space of billions of possible choices. And that's where the second part of system comes into play, the machine learning-based program optimizer. So if you want to optimize this, if you want to explore this search space to get the best performing program, the simplest way that you can do is to do black box auto-tuning. The idea is that you can just throw different variance program on your target hardware, collect profile statistics, and try it again and again until you get a good performance model. This is a reasonable approach possibly because it actually makes sense to spend hours or days to optimize your program since those deep learning workloads is going to be deployed for months or even years. But the problem is that this kind of black box approach have a very high experiment cost. and where each trials can take seconds or even more than 1 second to run, and you usually need thousands of trials to actually get, hundreds of thousands of trials to actually get a good performing sim. We can borrow conventional wisdom from database community to actually design a cost model to guide a search without having to try out so many times. The problem of this approach is that actually we do need to build a reliable cost model for each type of the hardware that we want to target. And given the complexity, I have to blame my computer architect friend that the complexity of modern hardware is so complicated that it's very hard to build an accurate cost model for each type of the hardware. So what we do is actually we take a learning-based approach, a statistical one, to collect history training data from the existing profiling statistics and use them to learn a statistical cost model that's instead being informed to guide the search or program optimizer. The advantage of this approach is that the statistical cost model can adapt to the hardware type that we are targeting on and make very fast predictions so that we can make very fast explorations just by querying the machine learning-based model while infrequently updates the model itself. To take a look at how much benefit we can get by using machine learning-based approach, I will show you one specific workload in ResNet 18, which is a common computer vision workload. Here, the x-axis is the number of trials we are throwing at the actual hardware, and y-axis is the number of speed up we are comparing against the baseline, which is a manually optimized CUDM baseline. We have two curves here. The first one is using black box random search, and the other one is using machine learning-based cost model. As we can see that machine learning-based cost model gives you faster programs by proposing less trials. And the really advantage here is that actually the statistical cost model can really learn what's going on and smartly guide you through the search space. So far, I have told you about how do we build each part of the system, in the sense that there is this high-level hardware aware search space and machine learning-based program optimizer. And now we want to ask what will happen if we combine both approaches together. So in here, we are comparing against, we are comparing on NVIDIA GPU dataset. Our baseline are TensorFlow and MXNet, both of which are backed by state-of-the-art deep learning libraries, CUDM. We also compared against TensorFlow XLA, which is the TensorFlow version of deep learning compiler. So in here, the y-axis is the number of times, so of single batch inference workloads, the lower is better. One of the takeaways that you can find from this plot is that XLA is not necessarily faster than the TensorFlow and MXNet. This kind of demonstrates the challenge of building actually competitive deep learning compiler for the system, in a sense that we have to compete against an entire team of NVIDIA engineers and Google engineers in order to really nail this problem. By using TVM, TVM automatically generates the code for each of the layers. And without graph optimization, we can already get quite competitive performance. And as I told you, because we automatically generate code for each of the layers, we can actually do a lot of graph optimizations, the high-level optimization together with a low-level tensor-level optimization. And that gives you a further performance boost compared against the baseline. There are two takeaways that you can find from this plot. First of all, on the leftmost side is the ResNet 18 workload. This is a very typical workload that all the engineers in the company who are working on deep learning models is going to optimize first. And what you can find is that TVM can already get very competitive model on those dogfight-like benchmark. The other more noticeable one is let's look at the model, the difference in the right, which is a deep Q-learning model. This model is used by DeepMind to play their Atari games. It's an important model, but admittedly, it's not as important or as standard as the ResNet 18 model. And what you can find is that we can get as much as 3 times speed up compared to the baseline. You can imagine what's going on here in a sense that engineers in the companies are paying attention to the most important benchmarks, while TVM is able to optimize on all the benchmarks because they can tirelessly try to use machine learning to optimize all the workloads. Our story you can find a similar story on other type of hardware. For example, this is an ARM CPU benchmark on Cortex A53, which is on ResNet. We are comparing against TensorFlow Lite. You can note that how a baseline name changes because as you change the hardware type, usually there's a specialized framework for that hardware type. While TVM is able to automatically optimize over the search space and actually get you the best performance on each of the hardware. There's also a workload. You can also find a similar improvement in the ARM GPU. If you go to our website or go to a paper, you can find more interesting results on more of the hardware types. So at the beginning of the talk, I've told you the story about me and my collaborator working on computer architects, working on deep learning accelerators. So far, I've only given you the result on CPU and GPU-like result. So what about accelerators? The good news is actually we do build one. This is called VTA, Customized Modular Deep Learning Accelerator Stack. So besides the components that I talked about today, including the search-based and ML-based optimizer, the VTA stack is a completely open-sourced hardware design that gives you customizable tensor intrinsics to perform like a TPU. It also have a standard ISA and a just-in-time based runtime compiler. We also provide a simulator so that if you don't want to run it on an FPGA, you can directly run it on your laptop. There are a few interesting highlights that I think is in particular interesting to system folks in here. In particular, the TVM VTA stack actually JIT compiles accelerator code to run on accelerator. It supports heterogeneous computation to run both on CPU and accelerators. And because we are doing the end-to-end design, we can move more of the complexity from the hardware to the software to keep the hardware simple while still gives you the flexible and optimized performance. This is a real true end-to-end full-stack open source design in a sense that we have an open source compiler, open source driver, and open source hardware design that you can run on your silicon. And I'm really excited about it because now you can use it as a testbed to do system researches like how do you co-design your system with your deep learning accelerator or just trying to improve the deep learning accelerator alone. So to conclude, TVM is this new novel approach of using machine learning to optimize machine learning system. We have demonstrated that by automating a huge part of system, we can really replace human engineering effort and get to the state of performance on broad range of hardware types. TVM is an open source project that's already been adopted by many of the companies, and I highly encourage you to check it out. You can find it in tvm.ai website. Thank you very much.
Thank you, Tianqi. Let's open the floor for questions.
Fan Yang from Microsoft Research Asia. Very solid work. I'd like to understand the tensor interface you proposed. That is there any reason you have brand new design for this kind of language, and is that possible to be compatible with existing programming interface like PyTorch or TensorFlow?
Yeah. So the question is about how compatible it is TVM to the existing frameworks. Actually, TVM is exactly designed to be compatible with existing frameworks in a sense that TVM can already take models from PyTorch, TensorFlow, and MaxNet and directly compile them to deployable modules on the target hardware. So the tensor expression language is only a middle layer that we use to bridge the gap, but the input of the system is actually high-level models from existing deep learning systems.
Thank you.
Zhibin Yu from Shenzhen Institute of Advanced Technology, Chinese Academy of Science. I have one question. You use machine learning to build the statistical cost model. So I want to know what is the algorithm you used? This is the first question. Second is, what is the accuracy of your model?
Yeah. So the question is like, what is algorithm is being used to build the machine learning cost model, and what is the accuracy? So to answer your question, there are multiple variants of machine learning model that you can use. Actually, we use two variants of models. One is the tree-RNN-based neuron deep learning model. The other is gradient boosted tree-based model, which is using XGBoost. In terms of accuracy, it really depends on how much training data that you can use to actually do the prediction. We are not actually predicting the absolute time, but relative order of the running time because we only need to rank them during the proposal procedure. But what we really care about is the end-to-end performance in a sense that how does the machine learning model help you to improve over the tuning cost.
Okay, thank you.
Hi, Chang Lan from ByteDance. Very nice work. So I was wondering whether the result will look like when you use deeper models like the ResNet 15 or 101.
So the question is like, what the result will look like if you use deeper model like ResNet 50 or 101. I would see the result is going to look similar in a sense that the ResNet 50 or 101 is only a more repetitive workloads of the current ResNet workload. So you will observe similar performance.
Okay, thanks.
Paul Barham, Google Brain. So the examples you showed in the presentation look a bit like a sort of tensor comprehensions kind of system for expressing pretty much one layer of a model. Can you say what TVM does if you had a large model that, for example, has huge numbers of intermediate values between layers that, due to computing gradients, and you want to do a whole program analysis about what's worth recomputing, what should be kept in memory?
Yeah.
Do you
So-
sort of optimize that?
Yeah, so the question is like what TVM will look like if you want to do something like gradient computation and optimize for memory recompute. Actually, TVM is a two-layer stack in a sense that we still have a high-level computational graph optimization that's being enabled by low-level code generator. So if you want to do like a memory dependency analysis and optional memory checkpointing, that is going to be done on the high-level computational graph layer, while the low-level tensor expression layer is used to generate optimized programs for the target hardware.
So you're saying that rematerialization and decisions are done at the high level,
Yeah.
and all the cost models at the low level?
Well, I can imagine that low-level cost model can still be useful to the high level as well, but so far, the cost model is only used to inform each kernel optimization.
Okay.
That's an interesting future work. Yeah. Thanks, Paul.
Hi, I'm Hao from Facebook. So my question is, what's the end-to-end latency in terms of the compile and optimization time?
Yeah, so the question is like, what is the end-to-end latency in terms of compile and optimization time? That really depends on, whether you already have historical training data or not, or like whether you already have pre-cached result. So in most of the common workloads, a common practice, if you want to just build services, actually you can pre-cache some of the training data and the workloads. That will give you a level of minutes of compilation time. But if you want to do things from scratch, it will take longer. But again, if you have historical training data, you can use that to pre-train a cost model. That will usually speed up your computation. And that's still an area of active research in terms of how do we use transfer learning technique to improve the speed up of automated optimization.
Yeah, thank you.
Thank you very much.